So I'm going to introduce Professor Thomas Schulthess. So Thomas is a professor of computational science, computational physics at ETH Zurich in Switzerland, and also the director of the Swiss National Supercomputing Centre. I did work with him for about 8 years when I was in Switzerland, and he won 2 Gordon Bell Prize Awards, 2008 and 2009. But most important for this audience is the person who introduced GPUs into the HPC world, right? So I remember going together with Thomas at this meeting in Zurich in 2010. We met with this small company. They were developing custom solutions in the embedded space, right? And at that time, Thomas had this idea of developing a prototype compute node with the GPU, the CPU, and the network card tightly integrated together, right? With zero copy memory access across memory spaces. That idea became Grasshopper 10 years later, right? And he has been working himself with NVIDIA. I'm pretty sure that he's been very influential in the design of that platform. And yeah, that's it. So please welcome Thomas to.
Yeah, let me just go with this. Okay. Thank you, Ugo. And this was a bit of a surprise that, well, I didn't check my email and then I didn't see that he asked me to give a talk today. And then he gave me a long list of things that I was supposed to talk about. And I will do my best to stay within half an hour. And then you just need to cut me off. Yeah. Okay, so I will, and you didn't ask me about the title or anything, so I have just a generic title. But I will talk about PASC and I will talk about our vision of what we are doing. But as I told you, the vision is a talk in itself and I try to cover PASC as well. So, okay. So I will have to cut some corners. But let me start with some context so you understand when you talk about the future of data, you have to understand the physical context you're operating in. And then, of course, you also have to understand probably the science we are facing and dealing with in Switzerland. So we are here in Lugano, our data center, our facility. Administratively, we are part of ETH Zurich, that is in Zurich, which is an engineering school. We have a second engineering school in Lausanne, and you know Gilles Forestier and Jean-Paul Kneip is here. And then we have a set of national labs, and altogether this is the ETH domain. And that's where we belong to. From a network point of view, we have a very strong academic network in Switzerland. And the relevant part here is today, we operate, anybody who needs to can at an affordable price operate about 400 gigabits per second. So that's what we do. Error Institute, which is up there also, and CERN, which is down here also. So we can have 400 gigabit per second sustained connections today. And the latency, you know, everything in Switzerland is roughly a few hundred kilometers, so latency is milliseconds, okay? And then we are, you know, it's a very reliable network, etc. We are geographically in Europe. I am repeating this because some of my countrymen in the US sometimes confuse Switzerland and Sweden. Both are in Europe, but Switzerland is in the center of Europe and Sweden is up in the north. So I don't know, what is this?
The monitors will turn off in 50 seconds and we'll just reboot back in. So just give it a second. Just give it a bit of time.
Okay.
There seems to be no way to turn off the auto power off.
And then okay.
And it'll just
okay. So
10 seconds.
Yeah. Okay, so so that what it means is that between us and one of our most important partners that you will see, ECMWF, that is moving from the data center from Reading to Bologna. So between us and Bologna, we also talk about millisecond latency. And you will also see that the Nordic countries, so Finland and Norway and Sweden, play an important role, and there we're talking about 10 milliseconds. Okay, now it's a good thing. Okay.
Sorry about that.
It's doing this how many?
It's the first time we organize an event like this here.
Okay.
This thing was completed like 2 weeks ago. So
Okay.
Now
Okay.
we're testing it out.
Okay. Good.
Yeah. We're basically using
Okay. So you know, between here, do you have a pointer or anyway? Between here and then Northern Europe, it's like 10 milliseconds, and that's roughly where we are. The most important is, of course, do we control or how reliable are these networks? And reliability of networks is very much depends on the politics, and the politics, of course, is not so simple. Okay, you don't see much, but anyway. This is, by the way, this is Anders Jensen. He's the managing director of the Euro-HPC joint undertaking, giving a keynote at ISC. And I'm very grateful that he highlights Switzerland in the middle of Europe. He's not doing such a good job with Great Britain, but we all know that Great Britain and Europe have a bit some issues at the moment. And then as a corollary of this, Switzerland has some issue. That's why we are both white. We are politically, we're like in exile. And that's what we have to deal with right now, unfortunately, the situation. Now, CSCS itself is the mission that we are given is develop and operate high-performance computing and data research infrastructure. So research infrastructure, we are not an IT shop that supports world-class science in Switzerland. And we have a user laboratory. So I told you about this Paul Scherrer Institute, which is a site that has a synchrotron, a user laboratory. It has a free electron laser, a spallation neutron source, and a muon source. So 4 user laboratory, and the 5th one is CSCS in Lugano. And the user laboratory is open access research infrastructure. And we operate 2 things. One is the user program, which people can access through a peer review process. This is something we set up 14 years ago when I started at CSCS. Today has roughly about 2,300 users, about 150 user projects from all over Switzerland, about 25–30% international users, so non-Swiss users. And then the second thing is this PASC program, which stands for Platform for Advanced Scientific Computing. I will come back to this. This is the focus of this program is to enable the research groups in Switzerland to develop HPC software, scalable software that works on advanced architectures. And it's probably one of our smarter investments. It's relatively low compared to the cost of the machines. It's maybe an order of magnitude less. It's very difficult to manage because scientists prefer to do whatever, not to focus on HPC software development. And so that's the part where even after 14 years, I still have a lot of homework to improve the focus on HPC developments. You can see the number of projects that we support has been steadily going up. And this curve is pretty much reflects the size of science in Switzerland. It also keeps going up. Now, it could be that now with the Ukraine war and all the financial crisis, inflation, maybe things will flatten off for a while, but I'm quite sure things will continue to grow. Now, one aspect that we have at CSES that is different from most HPC places is that we are also designing, building, and operating the system that runs the numerical weather prediction for Meteor Swiss. So we are very much linked to the weather forecasting. We do not do the weather forecasting ourselves, but we do all the HPC aspects of weather forecasting is what we are doing. Yeah, and that then also explains why this has such a relevant position at CSES, is weather and climate as a topic. So the center, like Hugo said, I started in 2008. In 2012, we moved into a new building, and I know you have created a new building. I was here last 10 years ago, 2012, and so a lot must have happened in the last 10 years. So we started with a new building in 2012. PIT-Stein is the system that's pretty well known by now. It's one of the first, so I was not the one that introduced it in HPC. We were, though, in Oak Ridge. I was still in Oak Ridge when I proposed to create the GPU system in 2008, and I got a long list of reasons why this is never going to work. Mm-hmm. And then in 2009, in Oak Ridge, we started to plan what then later became Titan. And well, we had to deliver a beta follow-up system in Switzerland. That was the beginning mission. And we actually went on PIT-Stein a step further than probably any other system. We ended up running 2 different platforms on PIT-Stein from about 2017, 18 onward. We had what I call the service-oriented architecture model, where we had the HPC platform, that's the user program I was talking about, and we had the grid middleware running for the LHC data analysis. So the Swiss Tier 2 and Tier 3 systems were all running on PIT-Stein for the last 4 or 5 years in production. It's like the first time we did this, it was a bit of a pain because the CX systems are not really built to run multiple platforms on one system. Okay. Then we did the PASC conference, and we did have one in 2022. So we had from 15 onwards every year a PASC conference. And then I think around this time frame, it became an ACM conference. The only year that we missed was 2020 because of the pandemic. We were the first, not just to introduce, among the first to introduce GPU-based systems in science, but we did for weather forecasting. So since 2016, our forecasting model, and I will come back to this, has been running on the GPU system. And we were a tier 0, where now this is in the past because EuroHPC decided to kill the Praise 2 program. So unfortunately, at the moment, we don't really have a very strong program in Europe for transnational access. But we know how to do it in Europe. We did it for the last 5 years. And we have also further developed the weather system into what we now call a software-defined infrastructure. So this is the devolution from doing things by hand here to do things with some level of automation. And I'm not going to cover this in the talk, but it's an important topic for what we plan to do in the future on the Shasta infrastructure. And today, of course, the relevant systems are the LUMI system and the ALPS infrastructure. Now, the key point here is, and I've said it before, during all the time, starting when I came in 2008, we always had a significant investment that we did in application development. We started with something we called high performance, high productivity computing, HB2C platform. For 4 years, we were asked to renew it, but we had to change the name. So we did PASC. We called it Platform for Advanced Scientific Computing. And we've been continuing this all the way to 24 is the current funding. And I got the reviews already for our proposal, and I'm pretty sure we will get funded at least to 28. And this is a fundamentally, a key part of developing HPC as a research infrastructure. One thing I have to say about LUMI, because you saw the Switzerland being white from the point of view of the European Commission, we are part of the LUMI consortium. So we have a stake in that machine. And you all know Colin, probably, or many of you know Colin, and he was on my behalf running or helping to run the LUMI procurement. And we are where we are, I think, very much thanks to Colin that I could delegate to that project. So we are a stakeholder, and there's not much politics can do about that at the moment. So just so you understand why LUMI is, don't need the music. So now let me go back to the challenge in weather and climate science is you have to manage very local scales. So you can see this thunderstorm, this is maybe a couple of kilometers across the storm that you need to resolve in the model. And at the same time, you have to resolve, the entire planet, okay? And another thing, for example, in Switzerland, is that the other storm was in Austria, but you can have the same thing over any of our lakes or system. What you have here are two valleys. This is actually the north-south, so this is Leventina, and this is the Urnersee, so north of the Gotthard, south of the Gotthard. These are valleys that you need to get the winds right if you want to predict weather in Switzerland. It's like the Santa Ana winds in if you know the LA basin. If you don't get those right, you're not doing good with predicting the forecast for Southern California. And here again, if you don't resolve this kilometer scale, you have no chance to do a good job. So this is a 2-kilometer model which we were running at the time. That was the innovation in 2008. This is the diurnal cycle, average diurnal cycle of the wind speed measured, and the 2-kilometer model. And then just by resolving this orography better by going to 1 kilometer, you basically fix the quantitative differences. And so with this, I want to show why we had to be doing very high resolution simulations already in production very early on, 10 years ago. So this was in 2013, Meteo Swiss telling us what they wanted to do, namely increase the resolution from 2 to 1 kilometer, increase an ensemble, at 2 kilometer, improve data assimilation. So they wanted us to improve the performance of the numerical weather forecasting system that we were designing with them and then operating later by a factor 40. And they wanted this to happen, a factor 40 in the system we introduced in 2015, when the last system that we introduced was 2012. And Moore's law at the time was still kind of okay, but it would not give you a factor 40 at constant cost. Okay. So that's when we were benefiting from the HB2C and then later PASC program, where we were already refactoring this weather model Cosmo. So going from a pretty much monolithic Fortran jungle into a well-structured software infrastructure where we replaced the dynamical core, rewrote the dynamical core, introduced domain-specific libraries that could hide the complexity of the different architecture. At the time, it was multi-core Xeon Phi, CUDA GPUs, and even ROCm-based or AMD GPUs. This worked very well. I'm skipping the details, of course. It was, a lot of work over maybe 5 years that then allowed us to address the problem. And it is interesting to see where all the improvements come from when you do a refactoring project. So about the factor 2 just comes from refactoring old software, adapting the way you manage memory, for example. That's pretty much what it was, not pre-computing parameters, but compute on the fly, because the memory architecture from the vector machines in the 80s has changed significantly. Then you have mathematical improvements. That's when you write the software and you're on top of it in terms of unit testing. You can do things more aggressively, like play around with the precision, etc. Then we had this shift from CPU to GPU, and that was pretty much taking care of a factor 10, and we had a factor 4 where we had Moore's law, and then also had to buy a few more nodes than we had before. But because we were moving to commodity architecture, and GPUs at the time were still cheap, so it was all affordable, and we did it. But the main point is there is no silver bullet. You have to work at many fronts. And the bottom line was, doing this whole exercise improved the performance by a factor 10. And this is cost versus performance, which was very significant for Meteor Swiss. And then and this is then NVIDIA marketing, coming in because they had to show that GPUs at the time can be used for serious business. And this was in 2015 when we introduced the hardware. The same system is then used even today still to run in production research projects. This is a high-resolution study of cloud formation in the mid-Atlantic, tropical Atlantic. And this is of Christoph Scher, his PhD student, that doing the study. These are the 50-kilometer resolution type of climate models that typically run, and this is a 3-kilometer model. And you can see significant differences. One of the things that I think most people can relate to is this formation of hurricanes. Let me see, there is one. Yeah, you can see it in the high-resolution model, and the low-resolution model is just white stuff, okay? And the fact that the ECMWF, with these low resolution, they are around 10 kilometers now, does okay with predicting the paths, is because of their data assimilation. So you can always fudge a model to do things if you know a hurricane is there. But if you want to study how they are formed, you need a high-resolution model. But the main message here is not that I'm not a climate scientist, so I shouldn't be talking about this stuff and trying to appear like competent. The main message here is we have the software that we develop both on the science side, basic research side, and on the production side, going hand in hand. It's the same investments, and you have to do this over many years. It's been a decade now that we have been investing in this. And of course, in PASC, we have more than just weather and climate. One area that is very important in Switzerland is material science and electronic structure. So we had a very similar approach. This is my own background, condensed matter physics, and so I know a lot more about this. I'm not going to say much, but we did introduce in my own group a library approach, a domain-specific library approach running with an LLPW method, exciting code. Then Joost van der Wonderlee is now my deputy director of science, so he's using it. He was the developer of CP2K, and we also had motivations with Quantum Espresso. So the same approach works in material science as well. This is work that was done with Thorsten Höfler and Joost van der Wondele and the people at CSCS, namely a library for matrix multiply that is communication optimal. And combining this library, and the matrices can be, not square, but can be these odd shapes that you need in CP2K. Combining this COSMA library with CP2K now, and all the, the performance portability and everything allows us now to run, get pretty spectacular results out of the LUMI, so the MI250 Shasta system, slingshot system. So we are talking about a problem that uses 1,000 bit Stein nodes, 1,000 GPUs before COSMA. So if we do the communication optimal, it looks better here as well. But this is showing the combination of algorithmic improvements and, of course, the hardware improvements to 16 LUMI nodes, which this is 64 GPUs. So, this is 1,024 down to 64. That's roughly the speed up that we get. And of course, between Pitstein, this was 2016 Pascal, and MI250 is now, roughly. So this is like 5 years of improvement in hardware and the algorithmic improvement. And this is really running on LUMI. There are real questions in Europe whether AMD, whether this works. No, it works, okay? And it also works for climate code. So we have an icon that we also developed the last 10 years, and we have the same story there. Icon is a bit more complicated right now from a political point of view, so I decided not to talk about that. So now I want to switch to the system side. I don't know if I still have
That's fine.
of time.
Go ahead. We'll let you know what.
So one of the trends that you see, and this really goes back to a decision that Dominic Ulmer and I had to make in 2012 when we saw we had this huge data center facility. And we said, okay, if we are going to ever fill this facility, we have to change the way we do things, because we had a much too small office building. Okay, we had this model of a team, a service, and a system. Okay, and then we were just multiplying those. And this would never work with the data center facility that we had. So pre-2012, and I'm just giving you a few systems that we had in Switzerland. CHIP is the Swiss Institute of Particle Physics. This was a tier 2 cluster standing at CSCS, separate of any supercomputer. We had Monte Rosa, which was the predecessor of Pitstein, flagship at the time. Schrödinger was a university cluster in Zurich. And Meteor Swiss is the systems I was talking about before. Okay. Then Meteor Swiss, when we moved into the building, became, I don't remember the name, but you probably do, of, I think, Lemma, Monte Lemma. Yeah, Lemma, and I don't know what the other one was.
Just want to let you know, in Switzerland, they name the systems after mountains.
Yeah, so Monte Rosa.
Yeah. The name of a peak.
Okay. Yeah. So you use the Maori, the native Australian sujets I saw on your shirts, and we use mountains as names. So then I told you about Pittscache that we introduced first GPU system. Then we had Pitstein that replaced this as the flagship, and we introduced a multi-core system, partly motivated to be able to cover university cluster in the same infrastructure. This was in 2014. And then in 2015, 16, 17 is when we merged PITSTINT and PITSTORA into one infrastructure. And when we also started the development to then eventually move the high energy physics cluster into this second platform on PITSTINT. So you can see we're going from different systems into one system in the end, okay? And what we had to do here is we did not have enough money. This is now the story after the one I told you before, when we had to go from 2 kilometer ensemble to 1 kilometer ensemble. We did not have enough money to buy the GPUs we needed to run 2 weather forecasting systems. There's always a main system and a backup system, okay? And so what Sadaf Alam then came up with the architecture that we have everything 2N redundant, but the compute nodes are just 1.5 times what we can afford. And we build one system that we manage, then have 2 partitions that can now be managed in software. Okay. So dynamically, so that's why I said going from what we did on here, which is manual, to here, is really a first step into a software-defined infrastructure in HPC. And I'm not aware that anybody has done this in HPC before we did. And this is a system that's been in operation now since 2020, was designed in 2018 and fully operational and very, very reliable. And we are now going to replace PITSTINT with ALPS, with this Shasta infrastructure. And so the HPC partition is 5,000 of these tightly, like you said, Hugo, nodelets on here, and we will have roughly 5,000 of these nodelets for the HPC user program on here. So the same, you know, this Grace and Hopper module. This is really, we've been working with NVIDIA since roughly 2020 in trying to put this together. It continues to be a struggle because this one doesn't exist yet. So we're in the middle of hoping, keeping fingers crossed that it will come, that we stay on time with the current schedule. But as you know, you have all these things like the pandemic and supply chain problems, etc. Now we have all this mess with Taiwan, etc. So we just have to keep fingers crossed that the world doesn't blow apart and we can build the system. Anyway, it turns out now from you know, so everything is on track, I would say. And now comes a new opportunity. And this is, again, coming from colleagues who work both in computer science and machine learning and in weather forecasting. So this is Thorsten Höfler and his group at ETH Zurich. Thorsten has been going into doing machine learning at scale and then working on this weather problem. And what they've been showing together with Peter Duben, who is at ECMWF, what they've been showing is you have these ensemble forecasts that you do in weather forecasting, that every ensemble member is a model trajectory, and you can train a neural network to learn these model trajectories. And then you can use a current simulation as like data points in this high dimensional space, and you use the neural network to interpolate. And so you can vastly improve the statistical forecast of an ensemble. So you can pretty much by an order of magnitude, apparently, you have to read the paper and believe them, but you can increase the statistical accuracy. So you can, like if you have 50 ensemble members, it's like you were running 500 ensemble members, okay? And that's an incredible improvement. That's like a factor 10 in terms of the size of the machine that you would need, that you can improve, okay? So this is a huge opportunity of improving things, but it exposes a problem namely, we can now start combining machine learning and end up numerical weather forecast, okay? And you saw before, and we can talk more about this, we are making our clusters elastic, okay? The problem is, on the weather forecasting side, this is not elastic, the workflows. They are made for a particular system. But the weather forecasters want to have elasticity, so we have to revisit the workflows, and then we end up having to revisit the whole software stack of how things are put together. And that is the struggle we're in since 3 years at CSES, is how to make things automatically deployable on this ALPS infrastructure. And it required us to reorganize the center, to take new technologies. So one that we've been working on since 2015 is the use of container technologies. And this is something that you probably know very well also. We had two views of the container world. One is on the HPC side with Shifter that we were contributing to, and Singularity. Then you have these Podman, Docker on the cloud side, and we wanted to combine both, and that's where we were developing this SARS container engine that I think Podman has now also taken over. It's an obvious way how you should do containers, namely use OCI bundles and particularly OCI hooks that you maintain on a particular infrastructure. and you can greatly simplify the whole runtime system that way. And so this is one of the parts that we focused on in developing and running on Pitstein. And here we are comparing molecular dynamics, deep learning applications, TensorFlow and Cosmo, NWP. And in all cases, the story is pretty much the same. When you can run at scale with containers, and you get even a slight improvement in performance. So no loss in performance, it's a slight improvement, typically because you have better control over the software stack when you work with containers. And then there are, of course, all the other advantages that you have with containers. So it's a technology that really works for HPC, and we've been funded when we were still at peace with the European Commission to productize this in the right way. Another area that we've been investing in a lot is to make the infrastructure programmable, so define RESTful APIs and that you can provide an interface to the entire infrastructure, storage, queuing systems, everything. And so that's a second area that we've been gaining a lot of experience with. And then there are a number of things that, I'm cutting things short here, that you also have to look at, namely this infrastructure as code, or what we call vCluster, versatile software-defined clusters, that we are currently developing on ALPS, which ALPS means Shasta CSM infrastructure, so collaborating with HPE on this. Then workflows. So I told you that the workflows of many applications are static today. And if you want to take advantage of containers, infrastructure as code, etc., you actually need to work on your workflow engines. AIDA is one that was developed at EPFL in material science, and we're going to use this. This is now my ambition, to use this and all the knowledge we have here as a backend to any workflow engine. So the ones, for example, they use EasyFlow and auto-submit and so in the numerical weather prediction world. And then you need to connect supercomputing infrastructure with data lakes and edge infrastructure. this is one of the things I believe you must be working on here with SKA. We are working with ECMWF as the data lake, and of course, also at Meteo Swiss, there is a lot of edge infrastructure, you know, all these radar stations they have, etc. So that's another topic that we could discuss also tomorrow, or no, Monday or this afternoon, whatever the program is that you set up for me. And then the last topic is this data flow centric optimization of HPC applications. So the main lessons that we learned is from, I don't know now, 12 years of collaboration with particularly weather and climate areas, refactoring software to take advantage of accelerated computing architecture. That's a key part that will stay with us. It pays off to introduce domain-specific libraries and development of frameworks for particular domains, and we have experience in a number of domains, also outside of weather climate. Then the software has to be deployable on heterogeneous infrastructures and across many infrastructures. We start with ALPS in Lugano. We will extend to EPFL and Paul Scherrer Institute and to LUMI and to ECMWF. And then we can talk about things with Pawsey. Yeah, I'm finished. Yeah. So and then you want programmable access to HPC resources and containerized deployment and automate workflows. Yeah, that's it.
Just wanted to say something because I attended one of the. I think they can hear me anyway. So I attended one of these PACER meetings, right, in the past, and someone was asking, why cannot I do what I do on the cloud on your systems, right? Pretty much, right? That's the question. The reason is because we don't have yet the infrastructure that Thomas just presented, right? But the plan is to really embrace that as well here, right? So that's it. That just want to say that.
And I think we might have time for one or two questions. Are there any questions?
Sorry, am I allowed to ask a cheeky question? Do you know where the first European-based exascale machine will be launched?
I think whatever I say now, I get myself in trouble.
All right, that's okay.
It is not going to be out. Okay, depends on what you define, how you define exascale. Okay, so we already have, I'm pretty sure, well, I don't know about AI flops on LUMI, but definitely ALPS will be massive when it comes to low precision arithmetics. So it will be many exaflops. And that's what NVIDIA was also marketing since last year when we announced the system. If you talk about HPC, so 64-bit HPL, we will find out. I know the plans, according to the commission, is in Jülich or in Germany. Jülich, we know now in Jülich is going to do one and one in France. And now it's the French and the Germans fighting it out among themselves. And that's good for the rest of us, because when they are busy with themselves, then the rest of us can do our work. And,
so it's really exciting to hear what Meteo Swiss did, but kind of introducing GPUs. Has there been any interest from kind of other weather centers, ECMWF or others, to kind of to leverage that work? Because it's not based on the unified model, or is it? Or?
No. Okay, so the unified model, that's Met Office. Okay.
Right.
And they are doing now the successor to the unified model is called Elfric, or what some name. Elfric is somehow a part of the project. There was gung ho,
still CPU
long
though,
study, etc. Well, but they introduced the whole thing with domain-specific libraries, framework there. I think that's the Elfric part.
Okay.
And that's there in order to be able to also go towards GPUs and whatever else in the future. There is a lot of interest now in the German weather service, Italian weather, actually Italian weather service without making big announcement has been using the Meteo Swiss, our investment in Cosmo to run. So the Italian weather services, they are running on GPUs. Emilia Romagna, Italy, you have to ask Hugo, it's complicated. Also, like everything in Europe. And so, and now they are working with us, yeah, to adopt. So there is a project within this whole Destination Earth thing, because we were thrown out. And so the Germans and the Italians and the Swiss partner in a project called GLORY, Global to Regional Something Modeling, based on ICON, using all the GPU technology that we developed. And yeah, so it's happening. It's just with maybe 5 or 10 years delay. That's
Very exciting, though.
yeah.
Thank you.
Was there one online?
Any other questions?
I find very interesting running a production service for the weather forecast while at the same time supplying service units to the researchers every year. So there are two very different models. I don't know at the moment very much about how a production weather forecasting job can work, but I guess it runs continuously or almost continuously.
Yeah.
And then
So you need to provide high availability with very strict SLA and so on. However, this is not unusual in the computing world. So there are, so from a facility point of view and from a data center infrastructure, and ALPS is no longer a computing system. ALPS is a data center infrastructure, the way you have to see it. And so you need to organize things to make sure that, for example, in your management plane and your management systems are sufficiently redundant, so that the cluster that we have with Meteo Swiss is not going down. If it goes down, there is one that we can spin up immediately, and so on. This is all possible. One of the reasons I was a bit upset that I see some of the HPE guys here is we're not there yet. And we have to really work on it very hard to make something.
Some focus, right? We stole 2 of the systems engineers from HPE who were working at CSCS and brought them here, right? That's why.
So that's probably already made my trip here worth it. But, I would not know that if I wasn't here. Okay, but no, you need to pay attention. And so from a system architecture point of view, you have to pay attention to a number of things. Yeah, but they are not, I think they will benefit everything because, for example, we also run what is called the materials cloud on this. This is this project from EPFL that had this AIDA workflow and a number of other things. And the materials cloud, on one side, there is an HPC part that's scalable, that uses a big infrastructure footprint. But then there is the data access and a number of services that have a much smaller footprint, but should be high availability. Now, once we learn how to do high availability for Meteo, we will have infrastructure to do high availability also for these cloud services or data services in other research domains. And so I'm convinced you can do both. It's not been demonstrated, so we have to, we will find out, but I'm pretty sure it will work.
Okay. Thank you. Thank you, Thomas.